Welcome to AI Paper Podcasts. Today we're diving into some really interesting, cutting-edge ML research. It tackles one of those things that just, bugs everyone about language model outputs.
You mean the repetition, the cliches, that feeling you get where you know it was written by an LLM?
Exactly that. The industry has a name for it now, slop. And this paper we're looking at today, it's all about tackling slop head-on.
Right. We're digging into Anti-Slop, a comprehensive framework for identifying and eliminating repetitive patterns in language models. And the core idea here is pretty striking. They found these repetitive patterns can show up like over 1,000 times more often in AI text than in human writing.
1,000 times. Wow. Okay, so this anti-slop framework is their proposed fix. It's got a few key parts. For everyone listening, especially the technical folks, let's quickly hit the three big innovations right up front. This is kind of our 1-minute summary.
Okay, sounds good. First up is the Anti-Slop sampler. Think of it as an inference-time tool. It uses this clever backtracking method and, crucially, a configurable soft banning strength to suppress patterns.
Soft banning.
Yeah, we'll get into that. But the key is it can handle thousands of patterns they tested, over 8,000, without the kind of collateral damage you see with, just crudely banning tokens.
Okay, so that's the sampler for inference time. But you need data to know what to ban, right? So innovation number 2.
That's their automated pipeline. This thing actually profiles the specific slop a given model produces. It compares it against human writing baselines and figures out that model's unique slop fingerprint.
And it generates training data from that.
Exactly. It automatically creates the preference pairs needed for fine-tuning, which means you don't need expensive humans labeling everything.
Super useful. Okay, and the third piece. This sounds like the one for making the fix permanent.
That's Final Token Preference Optimization, or FTPO. It's a completely new fine-tuning method. It takes the data from the pipeline and surgically updates the model weights. It adjusts individual token logits, the raw scores before probabilities, based on those inference traces.
Right, and the headline result. That's the really eye-catching part.
Yeah, this is the big one. FTPO achieved a 90% reduction in slop. And this is critical. It did this while maintaining or even improving performance on standard benchmarks like MMLU, GSM-8K, and writing quality evaluations.
Okay, wait, 90% suppression without hurting performance? That's huge. Because usually when you try to fix these stylistic things, especially with methods like DPO, you expect to take a hit somewhere else, right?
Absolutely. That's often the trade-off. DPO, for instance, tended to suffer pretty significant quality degradation when they push it this hard on the stylistic fix. So yeah, that 90% number with good performance is a massive claim for FTPO.
Okay, so to really get why this is such a breakthrough, we need to understand the problem they're quantifying. Before this, we sort of felt LLM text was repetitive, but they put numbers on it.
They did. They defined slop empirically. It's about statistical overrepresentation. They use this frequency ratio, denoted by rho, which is basically the frequency of a pattern P in the LLM's output divided by its frequency in human text.
Sure.
Simple ratio. And when you apply that, well, the examples in the paper are kind of wild. What was the most extreme one they found?
So they looked at creative writing from Gemma 312b, and they found this one character name, Ilara. Get this. It appeared 85,513 times more often than you'd expect based on human writing.
85,000. Seriously, that's not just a preference, that's like an obsession baked into the model.
It really shows these models can develop these very specific, almost intic-like habits. And it's not just single words.
What about phrases?
Oh yeah, cliches are a big part of it. The trigram heart-hammered ribs, a classic overwrought phrase, popped up 11,192 times more frequently.
And you see these clusters of slop, right? Things like sensory cliches, voice barely above a whisper, that sort of thing. Or intensifiers, like a profound sense of, and even sentence structures. They found this, it's not X, it's Y. Construction was like 6.3 times more common in some models.
So you end up with this predictable, quantifiable fingerprint that screams AI. And this is why just trying to ban tokens fails so badly, right?
Exactly. Token banning is just too blunt. The example they give is great. If the word catatonic gets tokenized into, say, cat, a tonic, banning that specific sequence to stop overuse of catatonic might accidentally stop model from ever using any word starting with cat. It's just not precise enough.
Right, collateral damage.
Yeah.
And just telling the model don't be repetitive in the prompt doesn't work either.
Usually not very well. It's the classic pink elephant problem. Telling someone not to think about a pink elephant makes them think about it more. It can make the pattern even more salient to the model.
Okay, so we need precision surgery. That brings us back to the first tool, the Anti-Slop sampler. It works at inference time. You mentioned backtracking. How does that actually work if the model's already started generating the unwanted pattern?
Right. So let's say the model generates the first token of a banned phrase, like the heart in heart hammered ribs. The sampler detects this, but instead of just stopping, it effectively hits undo. It backtracks to the point before it generated heart.
Okay.
Then it applies a penalty specifically to the probability of picking heart again. This penalty is controlled by that band strength parameter, S. It makes heart less likely.
And then it just tries again.
Yeah, it resamples from this newly adjusted probability distribution, and it uses smart techniques like min filtering to make sure whatever it picks instead of heart still makes sense in the sentence, maintains coherence.
That backtracking seems key. And the soft banding you mentioned, using the strength parameters, Mark, why is that configurability so important? Why not just always ban the bad patterns completely?
Good question. Because sometimes, believe it or not, the slop phrase might actually be the right phrase for the context. Imagine you explicitly prompt the model, write an essay comparing different kinds of tapestries.
Okay, yeah.
If you had a hard ban on the word tapestry because it was identified as slop in other contexts, the model couldn't fulfill the prompt. Soft banning allows the model to override the ban if the probability for that token is overwhelmingly high because the context demands it.
I see. So it suppresses it in general use where it's just a bad habit,
Right.
but allows it when it's genuinely needed.
Precisely. They found the sampler got almost 100% suppression in normal creative writing, but correctly allowed the patterns when they were explicitly part of the prompt. It prevents the model from breaking down.
That's really clever flexibility. But,
Sure.
okay, there has to be a catch. All this detecting, backtracking, resampling, that sounds computationally expensive. What's the hit on speed, on throughput?
Yeah, that's the major drawback of the sampler. It's significant. They benchmarked it using VLM for parallel generation, just banning 1,000 patterns cut throughput by 69%.
Oof, 69%.
And it gets worse.
Yeah.
If you use their full list of 8,000 identified slop patterns, throughput plummets by 96%.
Wow, okay, 96%. That basically makes it unusable for many real-time applications.
For high throughput scenarios, yeah, it's just too slow. And that is the core motivation for developing the second solution, the permanent one, FTPO.
Right, final token preference optimization.
Yeah.
Bake the fix into the model itself so you don't pay that inference cost every single time.
Right.
And the neat part is how it gets its training data, right? The sampler feeds the fine-tuning.
Exactly. It's a really elegant loop. Every time the sampler backtracks because it detected slop, it logs what happened. It captures the context, the rejected token, the first token of the sloppy phrase it wanted to ban, and then the chosen coherent alternative tokens, the ones it picked after resampling.
So it's automatically generating these preference pairs. This token bad, these tokens good in this context.
Yep. No human labeling needed. The problematic behavior itself generates the data to fix that behavior.
Okay, but now we have to tackle the other big question. Why not just use standard DPO, direct preference optimization, for this? It's the go-to for preference tuning. Why invent FTPO? What does DPO do wrong here?
That's really the crux of the FTPO innovation. They argue DPO, while great for general alignment, struggles with this kind of very targeted surgical suppression task. When you train DPO aggressively to just push down the probability of one specific bad token sequence,
It breaks other things.
it can, yeah. It can lead to model instability, it can actually reduce overall diversity in the output, and crucially, it can cause what they call unconstrained logic divergence. The internal scores for tokens can go haywire. FTPO is designed specifically to avoid these pitfalls using a few clever soft touch mechanisms.
Okay, let's unpack those. What's the first mechanism? You mentioned logic space earlier.
Right. First, FTPO works directly in logit space and uses mean squared error, MSE loss. DPO typically works with log probabilities and KL divergence. Working with logits and MSE helps to localize the changes.
Meaning it only tweaks the scores for the specific tokens involved.
Pretty much. It avoids putting pressure on the probabilities of totally unrelated words in the vocabulary just to make the math work out. It keeps the intervention focused.
Okay, that makes sense. Contain the blast radius. What else?
Second, the main preference loss term has this really neat margin-based deactivation. It pushes the logit score of the chosen good token to be higher than the rejected sloppy token by a certain margin. Let's call it MIM.
Yeah.
But, and this is key, once that margin is achieved, the loss effectively switches off for that specific instance. It stops pushing.
Ah, so it doesn't keep trying to make the good token infinitely better than the bad one.
Exactly. It prevents overtuning. This self-limiting behavior is why they found FTPO could train until almost 100% of the preferences in the training data were satisfied without the model's quality degrading. DPO, in contrast, started degrading sharply after satisfying only about 40% of the preferences, likely due to that unconstrained logit issue.
That's really smart design.
Yeah.
Apply pressure, but know when to stop. Anything else?
Yeah, the final piece is a specialized two-part regularization. They treat the target tokens, the rejected one, and the chosen alternatives differently from the rest of the vocabulary.
How so?
They use a regularization term that gently keeps the logits of these target tokens somewhat close to the original model, but it has a zero penalty window, allowing them some initial freedom to move to satisfy the preference. But for all the other tokens in the vocabulary, they use a much stronger regularization that anchors them firmly to their original values.
So let the key players move a bit, but lock down everything else.
That's the idea. Prevent the entire distribution from drifting away while you're performing this targeted surgery.
Okay, wow. That's a lot of careful engineering to make this work. So let's get to the results. They compared FTPO against DPO and good old token banning. What did the numbers show, especially on writing quality?
The results are pretty stark, especially when you look at the quality evaluation using GPT-5 as a judge on a 0-100 scale. FTPO consistently achieved high suppression, 83 to 92%, depending on the number of banned patterns, with barely any hit to quality, like less than 1 point loss compared to the baseline model. And lexical diversity actually stayed the same or even slightly improved.
Okay, that's the benchmark. Now, how did DPO fare?
DPO got some suppression, maybe 80-82%, so a bit less effective, but the cost was huge, a 6 to 15 point drop in writing quality, and diversity clearly collapsed, falling progressively as more patterns were targeted.
15 points is a massive quality hit. And token banning?
Oh, token banning was a disaster, just as you'd expect from our earlier discussion. At 8,000 banned patterns, the quality score absolutely cratered, dropping down to like 28 out of 100, just unusable.
Right, so FTPO clearly wins on the quality suppression trade-off. Did they check if it messed up the model's core abilities, like reasoning?
Yep, they checked standard benchmarks like GSM-8K for math reasoning and MMLU for general knowledge. FTPO stayed within 1-3% of the baseline model's performance. DPO, again, showed degradation, dropping scores by 2-5% on those tasks.
So the surgery seems confined to style, not core capabilities. That's crucial. What about longer text generation? Does the slop problem get worse there?
It definitely seems to. They noted the differences were particularly dramatic in long-form generation tests. FTPO's quality score stayed clustered near the original baseline, while DPO's scores really scattered downwards, indicating the repetition issues pile up over longer outputs, and DPO struggles to fix it without damage.
That makes sense. And there was one more really cool result about stylistic fingerprints, comparing the model to human authors.
Yeah, this was fascinating. They took the slop profiles, the patterns, each model over or underused, and they clustered them. They included the baseline model, the FTPO-tuned model, other LLMs, and even profiles from human authors like Mark Twain and Jane Austen. The FTPO-tuned Gemma 312b clustered significantly closer to the human authors than it did to the baseline Gemma or other LLMs.
Whoa. So removing the AI-specific repetitive junk actually made its statistical writing style more human-like.
It strongly suggests that, yeah. By surgically removing those model-specific tells, they didn't just make it less annoying, they nudged its overall stylistic fingerprint closer to actual human writing diversity.
Yeah.
That's kind of the ultimate validation for this approach.
That really is. Okay, so let's wrap this up. For the ML engineers and researchers listening, what's the big takeaway here?
The main takeaway is that Anti-Slop offers this pair of powerful, complementary tools. You've got the Inference-time sampler for immediate, precise control, if you can tolerate the speed hit or only need to ban a few things.
Yeah.
And then you have FTPO for embedding that fix permanently into the model weights. It solves the speed problem and does it with minimal damage to quality, diversity, or core skills, which is something other methods seem to struggle with for this specific task.
It's a targeted, data-driven way to improve stylistic quality without resorting to blunt instruments or broad alignment techniques that might have unwanted side effects.
Exactly. It's about precision.
So the final thought then, this whole approach is fascinating because it's forensic. They quantify these subtle stylistic fingerprints of AI. If this method can identify and surgically remove stylistic slop, What else could it find? What other maybe more subtle domain-specific fingerprints, maybe in reasoning patterns or structure, or even subtle biases, could we potentially identify and eliminate using this kind of highly targeted surgical fine-tuning? That feels like a really powerful direction for future work.